Why do quantum computations suffer from accumulated errors? Imagine trying to balance a pencil on your finger. It's easy at first, but the longer you try, the more likely it is to fall. Quantum computers face a similar challenge, but with qubits instead of pencils. These tiny units of quantum information are incredibly sensitive. They can be disturbed by even the smallest environmental noise. This sensitivity causes errors to creep in during calculations. Over time, these errors pile up, making the final results less reliable. One major reason is decoherence. Qubits are like delicate soap bubbles. They can burst when they interact with their surroundings. This interaction causes the quantum state to degrade, losing the information it was holding. The longer a quantum computation runs, the more chances there are for decoherence to happen. Another factor is gate imperfections. Quantum gates are like tiny switches that change the state of qubits. These switches are controlled by very precise pulses and hardware. But no control system is perfect. Small errors in these pulses or hardware flaws can introduce mistakes. Since quantum algorithms often need many gates, these tiny errors add up quickly. Measurement errors also play a role. When you finally read out the qubits, errors can occur. Sometimes the measurement device misreads the state, giving an incorrect result. This can be especially problematic if errors happen at the end of a long computation. Crosstalk and leakage are additional issues. Crosstalk happens when qubits unintentionally influence each other, causing errors. Leakage occurs when qubits escape their intended quantum space, leading to further mistakes. These unwanted interactions make error correction more complicated. Unlike classical bits, qubits can suffer from correlated errors. External events like cosmic rays or bursts of energy can hit multiple qubits at once. These correlated errors are harder to fix because they affect many qubits simultaneously. The no-cloning theorem is another challenge. It states that quantum information cannot be copied exactly. Unlike classical data, you cannot simply duplicate qubits to create backups. This makes detecting and fixing errors more difficult. Because quantum algorithms often need many qubits and long sequences of operations, even tiny error rates per step can quickly add up. This accumulation can overwhelm the system and distort the final outcome. To combat this, scientists use quantum error correction. They encode a single logical qubit into multiple physical qubits. This way, if some qubits experience errors, the overall information can still be recovered. Surface codes are a popular type of error correction because they tolerate higher error rates and work well with two-dimensional layouts. However, quantum error correction only works if the physical qubits are reliable enough. If the error rate is too high, adding more qubits for correction can actually make things worse. That's why improving hardware is essential. Better qubit designs, shielding from cosmic rays, and improved control electronics all help reduce errors at the source. In the end, the reason errors build up in quantum computations is because qubits are extremely sensitive and cannot be simply copied for redundancy. Overcoming this challenge involves a combination of smarter error correction, error mitigation techniques, and hardware improvements. Only then can we hope to build quantum computers that can run long, complex calculations without losing accuracy.